stem cells. George has been very much willing to spend some of his time as well in the public policy aspects of this, has been an articulate and effective interface in terms of talking with the public, with the Congress, with other decision makers about what the opportunities are here and also about important policy considerations. He's been a real friend to NIH over the course of the past few years. He came and spoke to the Institute directors at a recent leadership forum. It was a wonderful opportunity to be able to pick his brain. He continues to be very helpful in advising us about our plans to, in the intramural program here, make a real focus on induced pluripotent stem cells by the recruitment of a director.
Very special, and I felt a real sense of excitement when I met with a number of your postdocs for lunch, that there are new and creative ways that the community is thinking about exploiting this new and incredibly exciting technology around cellular engineering and induced pluripotency. And my goal today is to tell a number of stories about how we're approaching the biology of reprogramming and pluripotency and using it model disease, but initially to explore this fascinating biology of turning a cell back from its specialized state into a reprogrammed pluripotent cell. But I'll also talk about some of the lessons we've learned about the limitations of disease modeling and the fact that there are still valuable lessons to be learned from modeling using embryonic stem cells, and indeed valuable lessons to be learned from reprogramming through somatic cell nuclear transfer. So the stem cell concept has found its way into medicine for decades. Hematopoietic stem cell transplantation is one of the great triumphs of modern biomedicine, and indeed we have curative therapies, but there are significant limitations, and applications outside of the hematopoietic system are limited, and I think that's where much of the promise of stem cells are. The real boost to the field came in 1998 when Jamie Thompson's group isolated human embryonic stem cells, a pluripotent cell, the cell with the potential to become any tissue in the body, and therefore offer previously inaccessible approaches to linking gene function to tissue formation, creating a buzz in the pharmaceutical industry that one might have novel cell-based therapies or novel approaches to toxicity testing using real human cells. But of course, much of the long-term ambition is to move beyond the in vitro tools to actually create cells for transplantation. So if it's taken the better part of the 20th century for chemistry to be turned to the service of medicine, that is, the production of small molecules and their delivery of drugs, I think part of the excitement of the next 100 years, and it really may take much of the 21st century, is to be able to harness cells as medicine. Now, embryonic stem cells, which we've now had for the past decade or more, are really generic tools, and they do facilitate research on generic issues. But much of what I'll talk about today is the long-term ambition of stem cell research, which is to capture the ability to make customized and patient-specific stem cells. Now, when I was at the Whitehead Institute, my laboratory collaborated with Rudolf Jaenisch on a proof of principle that we could indeed capture the sort of dual technologies of somatic cell nuclear transfer to create a patient-specific tissues. I hesitate to use the word cloning, but here we're talking about cloning cells, and technology for directed differentiation of these pluripotent cells into a tissue of interest, in this case, the hematopoietic stem cell. So in this case, our patient is an immune-deficient rag-2 knockout mouse, a model of human Omen syndrome, severe combined immune deficiency. And using tail-tip cloning, technology that had been pioneered by Teru Wakayama, where literally one simply clips the tip of the tail of the mouse, cultures tail-tip fibroblasts, and then performs nuclear transfer into an enucleated egg. The recipient's oroplasm acts upon the incoming somatic nucleus in a way not dissimilar from the way it would actively demethylate the incoming sperm pronucleus and ready it for genome activation. One generates this pseudozygote and artificially activate N1 cells, an embryo from which you could derive nuclear transfer ES cells. Now these cells would carry the gene defect of the parent, and through homologous recombination, one can quite readily perform gene correction. We demonstrated in this experiment that the gene-repaired stem cells could generate a cloned mouse which had an entirely intact immune system. But in a proof of principle, we then differentiated these into hematopoietic stem cells engrafted the mouse and restored partial immune function. It was partial circa 2002. We're now in a position where we can effect complete hematopoietic engraftment from mouse embryonic or induced pluripotent stem cells. But we're still limited because we are required to genetically modify these cells to drive engraftment. And one of the great goals of our lab, and I would embrace for the community, is to learn how to direct the formation of hematopoietic stem cells in a completely genetically pristine manner, both from mouse and human pluripotent derivatives. Now, our hope in the early part of the last decade was that we could effect the same kind of proof of principle using human cells and human nuclear transfer, but indeed, this has never been successful, in part because human oocytes are in short supply, but I think in large part because this is a very cumbersome and challenging strategy. I don't think it was ever a practical alternative for modeling a large number of diseases. I think our hope all along was that it would teach us the principles of reprogramming in such a way that we could get to the more direct and facile method of direct reprogramming. And this was, in fact, the substance of my original application as an NIH Pioneer Award grantee. And during the time that we were attempting to effect reprogramming of spermatogonial stem cells, which are really unipotent stem cells, quite closely aligned with the pluripotent brethren, the work of Shinya Yamanaka came forward and really revolutionized the field. Now, what Shinya had realized was that there were a small set of genes among the many hundreds that are specific to the embryonic stem cell that confer this property of pluripotency, the ability of this cell to maintain a naive epigenome in such a way that it could give rise to various tissues under different conditions. And he winnowed from a large set of candidates a highly selected mini library which could be delivered en masse as a retroviral stream, and with titers such that essentially you would affect the expression of any combination of those 24 factors. And he introduced these into an embryonic fibroblast, which was a fortuitous choice because these are the easiest cells to reprogram. And he engineered in that fibroblast a reporter system which allowed him to select for ES-like cells. And then in another brilliant embodiment of this